This is on page 15 in your notes, and it's kind of a tabular representation of our function, its first derivatives and its second derivatives, and we're going to use that information to do a rough sketch of the graph. There's a similar one in your homework packet, so you might want to write on this one that this is similar. I'm trying to find the packet here. I'm actually in the classroom today, not at home doing this. You're probably going to hear the lunch bells ring because it's 4th hour, but just ignore them. On your packet, page 7, there's a really similar one to this. Not identical, but page 7. If you're stuck on that one, look here. So I'm going to use the fact that I know some definite points on the graph, because remember, f of is just the y values at that x. So when we say f of 0 is 2, that means at 0, 2, there's a dot on f, and I'm asked to sketch a graph of f. So first thing I'm going to do is use those function values to plot some points. F of 1 is 0, f of 2 is negative 2, f of 3 is 0. Then I have to look at these two at the same time, because f prime being negative, really what that does is it tells me the function's decreasing, but I don't know. Remember, we have two ways a function can decrease. It can decrease and be concave down, or it can decrease and be concave up. So in order to get that curvature correctly, I really need to analyze both of these at the same time. So underneath here, I'm just going to say what this means. Between 0 and 1, I'm to be above the y-axis. I'm to be going downhill, so I'm going to be decreasing, but I'm going to be concave up. So decreasing and concave up, what would that look like? I need to be going downhill and part of a cup, so it's going to look a little bit like this. So again, looking at both of those at the same time helps me get the curvature down. Then in the next interval, I'm going to have a horizontal tangent line because the slope is 0. I'm going to be going downhill or decreasing again, which is going to give me negative y values, downhill, but now I'm decreasing and concave down because I have a negative second derivative. So then I'm going to go like this. What that's going to do is create kind of a plateau in here, not a critical value. I'm continuing to decrease as decreasing, then I continue to decrease, but I change the concavity there. Then in the next region, I'm going to be going uphill because I have a positive first derivative, so I'm going to increase. I have a positive second derivative, so I'm going to be concave up. Increasing and part of a cup means I'm going to do that curvature. I'm going to go like that. Creates a little cusp down there, which jives with the fact that at negative 2, I have no first derivative and no second derivative because of the cusp. Then at the end, I'm going to be increasing and concave down, so it's going to end like that. Kind of looks like a upside down and backward shark tail, or not. Next up, so we'll answer a couple of these questions. When a function f is increasing, what does that mean about the derivative? It's going to be positive. When a function f is decreasing, what does that mean about the derivative? It's going to be negative. When a function f reaches a maximum at a smooth point, what does that mean about the derivative? It's going to equal 0 there. It's also going to change from plus to minus on both sides because I reached a maximum. Increasing to decreasing means the derivative will change from positive to negative there. When f reaches a minimum at a cusp, what does that tell me about the derivative? Well, it tells me that it does not exist, but it still has a sign change of negative to positive. This function is decreasing over here, so it has a negative first derivative, and it's increasing over here with a positive first derivative. It does create extremum, it's just that it creates it at a cusp. When the function f changes from concave up to concave down, what does that tell us about f prime? So let's go underline this. When f changes from concave up to concave down, it's actually easier to answer this question. We know that when the concavity changes, and it says it changes from concave up to concave down, that a change in concavity occurs at those inflection points where the second derivative is 0. But what is the first derivative doing? Well, the second derivative has to change signs. So what that means is the derivative of the derivative graph has to change signs. So f prime, let's go write this down here, f prime must, and again, let's stop for a minute. I have f prime and I want to talk about a change in concavity. That means f double prime must change signs. Well, f double prime is the slopes of the slope graph. So if I'm going to be talking about the slopes of this graph, then that graph must change. This is the hardest question, I think, to answer. Must change from increasing to decreasing. And last step, when the derivative f prime has a positive slope, that means its derivative, because every slope is a derivative, so its derivative is positive. Well, what do we know about f double prime being positive? It means, well, f double prime is positive, but what does it mean about f? It means it's concave up. So that's it for that page. So over here, again, I told you the biggest thing to do is really make sure you understand exactly what you are staring at. Write it big and bold at the top. I'm staring at the graph of f prime, and this is similar to the ones I had you practice yesterday. So you should be pretty good at it. But what I do for people who are struggling with these is I tell them to make a sign line for whatever this is the graph of, because some people don't like to read off that graph. They prefer to answer their questions off the sign line. So I'll answer a few questions and then let's pretend I get stuck and I'm going to go, instead of looking at the graph, make a sign line. But first and foremost, it's important that I note to myself that I am looking for where this is the graph of f prime, not f. So where did f have a horizontal tangent line? Anywhere where its derivative equaled 0. But I'm staring at the graph of the derivative. So I am looking for where the y values are 0. Right here, right here, right here, and right here. So that would be at x equaling -5, -3, 1, and 4. Those are all places where the derivative equals 0. Some may be maxes, some may be mins, some might be neither, but they are all horizontal tangent lines and they are also all critical values. For what values does x have a relative minimum? Anywhere where f prime goes from relative maximum, anywhere f prime goes from positive to negative. I was going to stop and tell you something here. It says to justify with a sentence. I'm going to allow you to kind of abbreviate with the shorthand on here, but never ever do that on the AP exam. To write them out in full sentences on your homework makes your homework take twice as long, which isn't the intent, but make sure you know how to word these in a full sentence for the AP test and for your test on this chapter. We won't be abbreviating. You would say that f achieves a relative maximum at x equals -5, and that's it. At x equals -5. Why? Because that's where f prime changes from positive to negative. And you would say that this is where f prime changes. And you don't say it's where f prime changes sign, because f prime changes sign here as well. You don't say that's where f prime equals 0, because all 4 of these locations. So we do not abbreviate on the AP test or on any test. Go ahead and do it in this packet, except on the AP questions. There's a couple at the end. Now let's pretend we got stuck. Let's suppose there's a couple of you out there going, I don't get that. What we're going to do when you get stuck is go make a sign line for that graph and label the sign line. So we're going to get the sign line from the graph instead of from the algebra. On the last chapter test, I'd give you the function f and I'd ask you for its relative extrema. And you would take f prime, you'd find where it equals 0, and you'd put it on this sign line. So let's do that. F prime is 0 at -5, at -3, at 1, and at 4. And when we did it with the algebra, we went like that. We're just doing a different level of this by looking at it from the graph, but we can still interpret it with a sign line if you're struggling. And then we did a sign test algebraically on the derivative, but I don't need to do it algebraically because this graph is the graph of y equal f prime. Positive y is here, negative y is here, negative still, positive, and then positive. Again, I'm looking at the y values because the y represents f prime of x. So if I interpret this sign line, I've got, here, I want to see how much time I've been talking. Can't quite see it. I don't know. Anyway, on my sign line, what this tells me is everything I need to know if I don't want to look at the graph again. For what values does x have a relative minimum? Anywhere f changes from negative to positive. That would be at x equals 1. And again, if you justified that, you'd say this is where f prime changes from negative to positive. Or you could say this is where f changes from decreasing to increasing. At what intervals is f increasing? Again, if I have my sign line laying down here, I don't need to look at the graph at all. It'd be from negative infinity to -5. That's where f prime is a positive or above the x-axis. From 1 to 3, union. Let's union all of this, by the way. Union, actually that's 1 to 4. Union 4 to infinity. And you can't pool these together because at 4, the derivative is 0. Actually, there's a plateau there. Again, what's the function look like? It's going up, then it goes down, continues to go down, then it goes up and continues to go up. It kind of looks funky like that. On what values or intervals is f decreasing? Anywhere where f prime is negative. Graphically, it's below the x-axis. On my sign line, I can easily see that. So sign lines are kind of nice for those of you struggling reading the graph. For what values does x have a point of inflection? Now that I can't get from my f prime sign line because inflection points are about f double prime. But f double prime, again, watch what I'm going to do up here. F double prime just adds slope of my slope graph. So f will have an inflection point where f double prime is equal to 0. Technically where it changes signs, but this is also roly-poly. It's pretty easy. The slope of my slope graph will be 0 here, 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 and up here and here. It's all the relative extrema. That would be where f double prime equals 0. It's the slopes of the slope graph. And that's at what? -4, -3, -1, and 2, and 4. You would list those all out. When is f concave up? Well, we know that's where f double prime is greater than 0. But I'm staring at f prime. So for its derivative to be positive, it must be increasing because the slopes of the slope graph need to be positive. So I'm looking for where f prime is increasing, and you can list that yourself off the graph. I'm getting tired of scrolling all the time. And lastly, on what intervals is f concave down? Anywhere f double prime, algebraically, is less than 0. But I'm looking at the graph of f prime. So I need its slopes to be negative. So I need it to be decreasing. And again, let's go take a look at that portion of the graph, where that happens. This graph is f prime. So this is charting f prime right here. And f double prime would be the slopes. Just like if it was the graph of f prime is the slopes. If it's the graph of f prime, f double prime is the slopes. So f double prime is negative anywhere f prime is heading downhill. And that's the end. You have a super one. The quiz is open and active, and you should get 10 out of 10. See you tomorrow.